wonderful opportunity, and also thanks for attending this talk. My name is Rita Chakraborty, and today I'll be sharing some of my work done under the supervision of Professor Simona Gallerani at Scuola Normale Superiore, and my work is based on exploring supermassive black holes at high redshift with LISA, and also the possibility of counterpart electromagnetic observation. So the sorry. So the motivation of our work comes from the idea to investigate gravitational wave signals we would expect to detect by the Laser Interferometry Space Antenna, that is LISA, which is a space-based mission led by ESA to be launched on 2034 to detect gravitational wave in the millihertz range, with sources ranging from galactic compact binaries to EMRIs. We are interested to model the gravitational wave signals from high redshift, so by which I mean in the range of redshift between 5 to 12 massive black hole binaries, and also explore the possibility of electromagnetic counterpart detection of such gravitational wave events post-merger. We did it in order to gain a better understanding on the formation and evolution of massive black holes in the early universe. How did we do it and what results did we find? Well, let's find out, before which I'd like to briefly introduce supermassive black holes evolution. This brings us to the mysterious growth of supermassive black hole and why we are interested in it. So, black hole mass measurement through reverbation mapping in quasars around redshift 6 shows that the mass of such black holes can reach up to 2 times 10 to the power 9 solar masses in less than 0.7 gigayears, which is astounding to ponder how such massive black holes can exist in such a young universe. There are many models to explain the formation of such massive black holes. One of the most popular among astrophysicists is the direct collapse black hole scenario, where the idea is that primordial gas collapses without fragmentation. So, in a metal free environment with a typical virial temperature above 10 to the power 4 Kelvin to not form molecular hydrogen, and sufficiently large Lyman-Warner photon flux, which destroys the molecular hydrogen. Because molecular hydrogen efficiently cools the gas and can cause fragmentation, which is what we don't want in order for direct collapse black holes to form. So such fragment-free primordial gas collapse gives rise to heavy seeds of massive black holes between 10 to the power 4 to 10 to the power 6 solar masses, which can then grow to absurd masses by merging and accretion. So we use zoom-in simulations, GW3, to track simulated massive black holes growth by merging through their gravitational wave signals and accretion. We use two different feedback models where by feedback I mean which is a fraction of energy accreted by the black hole which is radiated away and coupled to the surrounding gas. We considered two resolution of simulations, one co-moving kiloparsecs based on the work of Barai 2018, where which represents the kinetic feedback, where the feedback couples kinetically through energy-driven winds with the surrounding media in either a spherical geometry, so with a half opening angle of 90 degrees, or by conical geometry with the black hole at the apex with a half opening angle of around 45 degrees. And secondly, a resolution of 0.5 co-moving kiloparsecs used by Valentini 2021, where agent feedback couples thermally and isotropically to the surrounding gas and no kinetic feedback is considered due to agent. What happens in a simulation is first a dark matter only low resolution simulation is carried out in a simulation box which is evolved from redshift 100 to redshift 6 using periodic boundary conditions. The most massive halo is then chosen at redshift 6 and re-simulated with a higher resolution or zoomed in. Here So within the framework of our simulations, how are the black holes seeded? A black hole, which is considered or treated as a collisionless single particle, is seated at the center of a galaxy whenever it exceeds a halo mass of 10 to the power 10 solar masses if it doesn't already have a black hole at the center. The seeded black hole mass is around 10 to the power 5 solar masses, and once seeded, black holes grow by merging and accretion. The central black holes are assumed to merge when their host galaxies merge due to hierarchical structure formation. When two black holes come near each other such that the distance between them is smaller than an assumed threshold distance value, which could be the softening length, for example, and the local sound speed in the interstellar medium is lower than, and the relative velocity between the black holes is lower than the local sound speed in the interstellar medium, then the black holes are assumed to merge. Here you can see the merger rates predicted by each simulation for each feedback model considered, plotted with respect to redshift. So on the top left panel, we have divided the different panels based on the chirp mass ranges considered. On the top left panel, we have chirp mass less than 10 to the power 6 solar masses, in which we have also considered contemporary literature to compare our results with. On the top left, we have considered the chirp mass range between 10 to the power 6 and 10 to the power 7 solar masses. On bottom left, we have chirp mass ranges greater than 10 to the power 7 solar masses. And on bottom right, I've shown all the chirp mass ranges shown together. So different resolutions and feedback can be differentiated based on the merger rates of the model, as you can see. In these feedback models, the merger rates depend on the relative distance of separation of the black holes as well as of the sound speed of the surrounding medium of the black holes, as I said. In the Asian sphere feedback, which is represented by the red line in each panel, the sound speed is higher and the black hole softening length is smaller as compared to the Asian cone case, which is shown by the blue lines in each panel, and this results in a higher number of mergers in the Asian cone case. We compare our results in the chirp mass range less than 10 to the power 6 solar masses with Hartwig Agarwal, where chunky simulation based on Ramsey's code is used, and we have compared our results with the critical Lyman-Warner flux associated with direct collapse black hole formation of 30 times 10 to the power minus 21 arcs centimeters squared per second per hertz per steradian. And for Susanna, we have considered two models of stellar feedback. First, the high feedback model with high star formation rate and hence rapid metal enrichment, where the direct collapse black hole formation stops earlier, so around redshift 18, and the low feedback model, where the feedback is milder and halos remain metal-free for longer. So the direct collapse black hole formation stops around redshift 15. So we choose our fiducial model with the merger rate between the extremal values with optimistic Lyman-Warner flux. Here you can see the coalescence mass distribution with respect to the mass ratios of massive black hole binaries in 4 feedback models, with the white space in the bottom right represents the non-analyzed binaries due to our resolution limits. And on top left, the white beams correspond to the binaries falling outside the detection window. In all cases, we see that the maximum number of events occurs for equimass binaries for low masses. So just seeded binaries have a higher probability of merging as compared to black holes, which grow to higher masses through merging and accretion. The signal-to-noise ratio for the gravitational wave events are estimated through the Flanagan and Hughes formalism. We keep the threshold of detection at a signal-to-noise ratio corresponding to 10, and we show the scatter map of the signal-to-noise ratio with respect to redshift and chirp mass for each feedback case. We find the frequency of detection is inversely proportional to the mass of the system. So for higher mass spectrum, the emergent gravitational wave frequency is lower, and from this signal-to-noise ratio, we calculate the angular resolution for the detectable events of our fiducial case to explore the possibility of complementary electromagnetic detection of the gravitational wave events. On the left, we see the fraction of events detectable by LISA for each feedback model. The detectable number of events is related directly to the mass distribution of the binaries in each feedback case, as I already explained. From the angular resolutions, we see that we have better prospects of localizing our gravitational wave events for low mass binaries at lower redshifts. And this localization is important for other electromagnetic facilities to follow up the gravitational wave event, which brings us to the possibility of detection of gravitation of gravitational wave events through electromagnetic counterparts post-merger. We use a distance threshold with each redshift bin for the coalescing binaries to associate them with a host galaxy and calculate the UV luminosity, which is the sum of the UV flux due to the star formation and aging, the X-ray luminosity, the far-infrared luminosities, and the CPS luminosities for the host galaxies. These quantities give us information about the star formation rate of the galaxies, the isotope properties, which can be explored to detect post-merger galactic changes. In the movie, you could see a galactic merger occurring, and our simulation models as well. Similarly, the central massive black holes merge upon galactic coalescence, and the new black hole is positioned at the center of the new galaxy. From all the events in our fiducial case, we select the events which are bright in different electromagnetic bands, by which I mean with a UV magnitude of at least -21, a far-infrared luminosity greater than 10 to the power 12 times solar luminosity, an X-ray and C plus luminosity of at least 10 to the power 8 solar luminosity to be detectable by various contemporary electromagnetic instruments of LISA, such as GW3 for X-ray and ALMA for C plus and the FIR, links for the X-ray, GW3 for the UV, and also with the detectable signal-to-noise ratio in the LISA band. We select electromagnetic facilities which will be potential contemporaries of LISA and see that especially for X-ray missions, the field of view is extremely small, and we can only make follow-up observations upon precise localization of the gravitational wave event. We also compare the range of sensitivities of different electromagnetic emissions and compare it with the spectral energy distribution of two electromagnetically bright and LISA detectable events, so with a signal-to-noise ratio greater than 10, to be discovered by electromagnetic instruments such as GWST, ALMA, Origins, etc. And finally, we create UV FIR maps of the selected events from our simulations that we would expect to see through eligible telescopes and present a panoramic view of the gravitational wave event detectable by LISA. To conclude, we saw that different agent feedback channels can be differentiated in direct collapse black hole formation model from the merger rates of the massive black hole binaries. Keeping a threshold of signal-to-noise ratio 10, which is quite optimistic, we find angular resolution of most LISA events to be poor. Upon relating with host galaxies of merger events and exploring the possibility of different electromagnetic facilities to observe post-merger galaxy, we present a panoramic view of the gravitational wave events and its post-merger scenario. So, to summarize, the gravitational wave detection with LISA along with the electromagnetic counterparts, would create a better understanding of galaxy formation and evolution. Thank you.
Okay, thanks a lot also for the nice talk and keeping really perfectly on time. So there are a few minutes for questions. Yes, Praktika, you can I think I have to unmute yourself.
Yeah.
Oh no, you can unmute yourself. Okay, go ahead, please.
Yeah, thank you, Philippe. So Srija, very nice talk. I was just curious, do you also consider light black holes from POP3 stars?
No, we only consider direct collapse black hole
Direct collapse black
scenarios,
holes?
only the
Yeah.
heavy seed models.
I see. Yeah. Okay. Now that makes sense because you're especially trying to look at these really massive quasars, right?
Yes,
Yeah.
absolutely.
Perfect. Okay. I just wanted to clarify this. Thank you.
Yes, thank you.
Thank you. Further questions?
Hi. Yeah. First of all, great talk.
Yeah, please go ahead.
Second of all, I was wondering what state you expect the counterpart galaxies to be in when these black holes are emerging. Like, should they be fully relaxed at that point, or will they still be in an active emerging stage?
Okay, so when we are detecting these black holes, we would so we are calculating the signal to noise ratio of this black holes merging throughout its inspiring state. And we are only looking at the electromagnetic events after the merger has completed. So we are focusing on the post-merger scenario through the electromagnetic events, but we are getting the expected localization of the black hole event right from the time it enters the Lisa band in its inspiraling phase.
Sure. So to clarify, like the galaxy itself, the merger process of the gas and everything outside of that.
So it should be an active phase.
Okay, cool. Thank you.
Yeah.
Thank you. Further questions? Okay, seems not to be the case. Then Srija, sorry for that.
Srija, no worries.
Okay, thanks a lot for your nice talk. Then I ask the next one. This is Pratika Dayal. I hope I also speak correctly.
Yes.
Please share your screen. You are also unmuted. So I would suggest, okay, even though we are 2 minutes in advance, maybe you can start. Okay. Please, the floor is yours.
Okay, thank you very much. Okay, so good morning, everyone. Thank you very much for being here. Very early in the morning for the Europeans. So yeah, I really appreciate it. Okay, so today what I want to do is just give you a very broad overview of the kind of black holes and the sort of event rates that we are expecting from LISA. And basically, I'm going to really concentrate on galaxies which were forming in the first billion years of the universe. So just to put this into context, the sort of galaxies that we are looking at are those which were really the first population 3 hosts that were forming in the early universe, because these could have seeded very light stellar black hole seeds of a few hundred solar masses. And of course, we are also going to consider these direct collapse black holes, which Srija has very nicely introduced. And so effectively, I'm going to focus on an era which is between redshift 40 and redshift 5. So this is basically the era which I'm talking about. So the rise of the first galaxies and when they start re-ionizing the universe. So basically, this is the era of hydrogen re-ionization. And the idea is that when you have star-forming galaxies or AGNs, for example, they start to produce ionizing radiation that can break up hydrogen into electrons and protons. And this is called the epoch of hydrogen reionization, which lasts from a redshift of, well, whenever the first stars start forming at a redshift of 30 or 13, depending on your favorite model for forming the first stars, down to a redshift of roughly 5 to 6. So, of course, I should mention that this work was done in collaboration with a number of excellent co-authors who are listed here. And this is the team in Groningen who are working on different aspects of high redshift galaxy formation, including black hole formation and growth. Well, so just to anticipate, the key idea behind these sorts of models is to have multi-messenger astronomy models with which we can make predictions for example, Euclid, but also SKA, and of course, link these together with LISA, or to already get hints from these on how many events you can expect from LISA, from models that are baselined against all the data that we actually have available. So let me start by showing you the theoretical model that we use. So this is called Delphi. And the whole point behind Delphi is the following. So this is a semi-analytic model. And we have chosen to go semi-analytic because this is actually the only way in which you can explore the entire halo mass range that is required. So at a redshift of roughly 4, we start by simulating halos between a halo mass of roughly 10 to the 7.5 to 10 to the 14.5. So we can really study an enormous range of black holes and their host galaxies, which is really not possible to do with any kind of numerical simulations alone. So our model includes all the key physics. So for example, at high redshifts, you start with low mass halos that merge or accrete gas from the intergalactic medium. They convert a part of this gas into stars. Which can push out some part of the gas from the galaxy. So you have supernova feedback. We also seed them some specific halos, and I'm just going to show you in a minute how we do this. So halos where you have metal-free stars forming can actually seed stellar mass black holes of a few hundred solar masses. On the other hand, when you have large mass halos, which are embedded in a large enough Lyman-Werner background, then those can actually host direct collapse black holes, which are somewhere between 10 to the 3 to 10 to the 5 solar masses. And for this, we explore different sorts of masses. So we also include black hole accretion and black hole feedback. This is very critically tied to the underlying mass of the dark matter halo that these black holes live in. And so we have really all the key physical processes of gas accretion, galaxy mergers, gas, stellar mass, black holes being brought in by mergers, and IgM accretion, of course. So this is a very small schematic to show you how these different black holes are actually growing through time. So for example, if you have galaxies, so I'm looking at the right-hand side of the merger tree. If you have galaxies that have a black hole, they can actually, if the halo mass is small enough and the mass of the black hole is large enough, these can push out a lot of gas from the galaxy. And so you are left with some kind of tri-merger at the next time step and so on. So all of this key physics is really taken into account in our model. So we have a number of different physical processes that we have explored. So as I have noted, we include 2 types of black hole seeds. So the first is from the collapse of population 3 stars, which yield black holes of a few hundred solar masses. And the second is these direct collapse black holes, which are very rare, but can be extremely massive. So they can be up to 10 to the 3 to 10 to the 5 solar masses. We have the impact of Re-Ionization feedback, which is a kind of feedback that preferentially affects low mass galaxies in the epoch of Re-Ionization. And I'm just going to show you in a minute why this is so crucial. We have black hole growth that is regulated both by the halo mass, so how much black hole feedback can you actually have, which will eject the rest of the gas from the galaxy. And this is a balance between this maximum value and some sort of a gas availability. So how much gas do you actually have for the black hole to accrete? So just to give you a very small example, if you have a very heavy black hole seed in a low mass halo, the moment this black hole accretes something, it will have a huge amount of feedback, kicks out the rest of the gas from the galaxy, and then it has to sit there until this halo either merges with another halo that has gas, or it can accrete gas from the intergalactic medium. So black hole growth and supernova growth are really closely tied together. Both of these are included in the model. And finally, something that is really important is on what timescales do black holes actually merge? So we consider 2 sorts of limiting cases. So the first is the moment dark matter halos merge, we assume galaxies and the black holes basically all merge. In the second scenario, dark matter halos merge, but galaxies and black holes merge after some sort of a dynamical timescale. So let me just start by showing you the total number densities of black hole seeds that we find. So here, this is the number density of black hole seeds per co-moving megaparsec cube as a function of redshift. The solid black line shows the number of stellar black hole seeds from population 3 stars. So you can see that basically by a redshift of 6 or so, we're predicting 10 to the minus 3.8 stellar black hole seeds per co-moving megaparsec cube. However, direct collapse black holes, which require many specific conditions, which include completely metal-free gas that is embedded in a high enough Lyman-Werner background that it doesn't cool and fragment, these are much rarer. So if you use a threshold of 30 times of J21, so these are arbitrary numbers, so I don't really want you to care about these, but what we are trying to look at is how does the number density of these direct collapse black hole seeds actually depend on the strength of the background? So here, let's say you assume a value of 30, the amplitude is 30 for the Lyman-Werner background. Then you find that the number density of these direct collapse black hole seeds is roughly of the order of 10 to the minus 5.8 per cubic megaparsec cube. So it's roughly 2 orders of magnitude lower than your stellar black hole seeds. A much more reasonable number is something of the order of 300 times of J21, which is the strength of the background. In this case, the number density is actually 4 orders of magnitude less than what you expect from these stellar black hole seeds. So the only point I would like to make from here is that stellar black holes really dominate in terms of the number densities of black holes, and direct collapse black holes are 2 to 4 orders magnitude less than these stellar black hole seeds. And to link to what Sruja has been talking about, these direct collapse black hole seeds were basically invoked to be the seeds of the most massive quasars we see at high redshifts, because otherwise we find it really hard to grow them, to grow seeds from 100 solar masses to 10 to the 9 solar masses in roughly 1 billion years. So of course, as you can already imagine, the caveat is that if you want to grow these really heavy supermassive black holes at a redshift of 6 or 7, somewhere in the first billion years, then you preferentially need to seed those halos with the direct collapse black hole seeds by construction. However, what I would really like to highlight, and this is something that we have been really trying to study a lot, is the effect of re-ionization feedback on galaxy formation. So let me just clarify what I mean by this. So what I'm showing you here is just a slice from one of our simulations, where the blue patch shows you hydrogen that is neutral. The goldenish patches show you hydrogen that is ionized. So in the regions where hydrogen is neutral, the temperature of the gas is roughly equal to the ambient temperature of the CMB. So at a redshift of 10, the temperature of the gas that is not ionized is roughly of the order of 33, 35 Kelvin. However, in regions that get ionized, the temperature can immediately rise to 20,000 or even 40,000 Kelvin, depending on the underlying sources. So now imagine that you have a low mass halo, which has a virial temperature of roughly 20,000 Kelvin. Imagine it is hit by this ionizing background, which has a temperature of also 20,000 Kelvin. What you can do is basically photoevaporate some or all of the gas mass of this low mass halo. And so this is basically what we mean by re-ionization feedback. And just to show you what this looks like, in the bottom panel, I have these two panels, and I would just like you to look at the right one in the interest of time. So here, what I'm showing you is the gas mass divided by the halo mass, so basically the baryon fraction, as a function of halo mass for 3 different redshifts, 6, 8, and 10. So the solid lines show you the result if there is no re-ionization feedback. On the other hand, the dotted lines show you the baryon fraction if, sorry, it's the opposite. The dotted lines show you the baryon fraction if there is only supernova feedback, and the solid lines are the baryon fraction when we include re-ionization feedback. So what you can immediately see is that for galaxies below 10 to the 9 solar masses, the moment you include the effect of re-ionization feedback, you can decrease the baryon fraction by a factor of 2 to a factor of 50, depending on the halo. So I would not like to go into any details, but if you're interested, the whole problem has been that how much re-ionization feedback can suppress the gas mass of any specific galaxy depends on the halo mass, the strength of this re-ionization background, the redshift of the source, and the redshift at which this assembling source was first hit by a re-ionization background. And so if you're interested, please feel free to ask me more about this later. But essentially, what we have tried to do is start by baselining our model against all the available high redshift data, which includes ultraviolet luminosity functions for both high redshift galaxies, so Lyman gray galaxies, as well as high redshift quasars. We have tried to match to the stellar mass densities at high redshift, black hole mass functions, and the black hole stellar mass relation. So this is a model that is really baselined against all the available data that we have at high redshifts. So let me just very quickly show you the stellar mass halo mass relation, stellar mass black hole mass relation. So on the vertical axis, I'm showing you the black hole mass. On the horizontal axis, it's the stellar mass. This is at a redshift of 5. What we find is that for galaxies which have a stellar mass larger than roughly 10 to the 9.5 solar masses, the black hole mass and stellar mass start scaling really well. And this is quite in accord with also what you expect at low redshifts. However, as a result of supernova feedback and re-ionization feedback, black holes in lower mass galaxies are finding it really hard to grow. So as you can see, they show this steep drop in the black hole mass over a really short range in your stellar mass. And this, the low mass tail that you see here, this is actually direct collapse black holes that are finding it hard to grow because they have no gas, because all the gas in these low mass galaxies has been ejected because of supernova feedback. When we include the effect of these delayed mergers, that introduces yet another delay in the growth of black holes. In the end, it really leads to a relation, at least for galaxies above 10 to the 9.5 solar masses. You can see that the relation is quite similar to what you have without introducing this dynamical delay in the merger of black holes. However, the scatter is much larger, and this is because different black holes are now, instead of merging instantaneously, they are merging on very different timescales. So now let me very quickly show you from this model what kind of event rates are we predicting for LISA. So this is the number of events per unit per year as a function of redshift. This is the maximum numbers that we would expect. So this is the instantaneous merger model. The purplish line shows you all the events that we predict. But then, of course, we have to impose some sort of a signal to noise when we talk about LISA. So we choose a value of 7, which is roughly what is done in the LISA collaboration. And what you can clearly see here is that most of these mergers for signal to noise larger than 7 are actually stellar black hole mergers. So these are stellar black holes which have gone from 100 solar masses to a few thousand solar masses. The next is stellar black hole direct collapse mergers. So these are called mixed mergers, where you have stellar black holes merging with the direct collapse black holes. Given their low number densities, as expected, the mergers between direct collapse black holes and direct collapse black holes are extremely rare. The situation is quite similar when you talk about introducing this dynamical delay. Effectively, what changes the most is that now we don't have any mergers between direct collapse black holes, because they really take much longer than you expect. And so they move out of this window. So they are happening at much lower redshifts compared to what we are considering. And of course, then we're interested in looking at the mass distribution of these mergers. So here, what I'm showing you is the number of mergers per year as a function of the merged black hole mass. Again, we start with the maximum number of mergers predicted. So this is from the instantaneous model. And what we find is that LISA detectable mergers with a signal to noise larger than 7 lie in within this mass range of merged mass between 10 to the 4 to 10 to the 7 solar masses. So these are the sorts of black holes that LISA is actually going to detect. As you can already imagine, most of these are stellar black hole mergers, and a small contribution is provided by direct collapse mergers. Again, the situation is quite similar. So the numbers are slightly lower when we introduce this dynamical delay in the mergers of black holes. However, what you are basically finding is that stellar black hole mergers are not as much affected, but there are no direct collapse mergers in this case. So just to give you an idea, here I'm showing you for all of these different models. So we consider different kinds of masses for our direct collapse black hole seeds. Please ask me more about this if you're interested. But basically, we are predicting anywhere between 12 and 20 mergers over a 4-year mission duration from LISA, from black holes at redshifts above 5. And the point that I would really like to make is that most of these will be dominated by mergers between stellar mass black holes from population 3 stars that have actually gained mass and entered this mass band between 10 to the 4, 10 to the 7 solar masses, with direct collapse black holes contributing a very, very small amount because of the fact that they are so rare. So let me very quickly give you the emerging picture that I have tried to present. So what I would just like you to take away from this talk is that it is really crucial to simultaneously model black holes and their host galaxies, because especially at high redshift, supernova feedback is really, really crucial in modulating the growth of black holes, especially in these low mass galaxies. And the second thing that is really important to take into account is the effect of re-ionization feedback, which can really photo-evaporate the gas mass from low mass galaxies. And because of this, black holes in low mass halos will find it really hard to grow, especially at early times in the epoch of ionization. Our model is predicting roughly of the order of 12 to 20 high redshift events between 10 to the 4, 10 to the 7 solar masses over a 4-year mission duration. And this is including the effect of delayed mergers, considering different kinds of masses for direct collapsed black hole seeds ranging between 10 to the 3 and 10 to the 5 solar masses. But what I would really like to bring to your attention is the fact that how and when you see black holes is actually really crucial. So as of now, we are making really simple approximations on which kind of halos can be the host for stellar black hole seeds, or which sort of a halo can host a direct collapsed black hole. But these have to be really improved in the future if we really want to have stronger constraints on these event rates. Another outstanding issue is on what timescales do black holes actually merge. So what I've shown you is just a dynamical delay, but actually what will happen is that the black holes, when they come together, they will harden into a binary, and then this binary will keep hardening, and at some point you will have your merger when gravitational waves are emitted. So this has to be really modeled in much more detail. And so what I would just like to maybe anticipate is the next step will be really to include these into n-body simulations. It will be really incredibly hard to get the mass range that we require from hydro simulations. And so the approach we are trying to use is to really use n-body simulations so we can really capture the entire range of black hole masses and their hosts, which we expect from LISA. So I would stop here. Thank you very much.
Okay, thank you very much, Pratika. Are there questions? We are perfectly on time, so if there is one or two questions, don't be shy. Everything is clear? Well, okay, then, sorry?
Oh, that is also fine. Yeah, I mean, people can always mail me if they have questions later. So yeah. Exactly.
There is maybe somebody like Andrew Cameron who is trying to. Oh no. Okay.
Okay.
No question. Okay, then thanks a lot again.
Yeah, of course. Thank you.
Stay tuned with our meeting here. And then I call the next participant or the next presenter, Rafia Sarwar. I hope I also pronounce your name correctly. I guess for you it's probably evening or something like that.
No.
Sorry?
It's morning. It's morning, 11 a.m.
Ah, okay. Okay. So we are not so much different. Okay, then please share your presentation, and then you can start. And as usual, a quarter of an hour plus 5 minutes. Okay, please go ahead. Maybe there is a bit of noise background, so I ask all others to mute themselves.
Okay. Can you see my screen now?
Yes. Maybe can you take?
Okay.
Okay. Yeah. Perfect. Perfect. Okay. Okay. Perfect.
Okay.
Start.
I will stop my. Okay, I will stop my video because I have some internet connectivity problems. So in order to go smoothly and avoid the disconnection, I'll turn it off. Hi, I'm Rafia. First of all, I would like to thank the organizers for giving me an opportunity to talk about our recent work. I recently graduated from the master's program of Institute of Space Technology, Islamabad, Pakistan, and currently I'm looking for a PhD position. In the meantime, I had been working with Florian, Simone, and Tassos from University of Geneva on galactic binary black holes. Before we get there, let me start with a few words about how binary black holes are formed. There are several formation channels proposed in the literature for the formation of binary black holes, including a family of models based on the isolated binary evolution. These formation channels include so-called common envelopes, stable mass transfer and chemically homogeneous evolution. There are many more, the most prominent of which are the ones based on the dynamical formation of binary black holes in dense stellar systems. However, in the rest of my talk, I will be considering only the first three. In the common envelope and stable mass transfer channels, one starts from the relatively wide binary, where the most massive star evolves first and becomes a supergiant. At this stage, it overfills its Roche slope and loses its envelope via stable mass transfer. Uh, at the end of the stable mass transfer phase, the binary becomes a stripped helium star that soon collapses to form a first-born black hole. If one assumes an efficient angular momentum transport, meaning that the stars are rotating close to a solid body, then the progenitor of the first-born black hole will have lost all of its envelope and to become a supergiant, and then loses its envelope via Roche slope overflow. Um, that's why the first-born black hole is expected to be born with a negligible spin. Now, when the secondary star evolves off its main sequence, and the whole process repeats itself in reverse, with the secondary filling its Roche slope. However, the mass ratio of the binary has now changed. If the mass transfer is again stable, then we strip once again the hydrogen envelope of the binary, and from the helium star soon collapses to form the second born black hole. In in the second mass transfer, the orbit shrinks. That might bring the two black holes close enough to merge within the Hubble time. If the mass transfer is stable, the binary goes into the common envelope phase, and the orbit shrinks dramatically and releases the orbital energy that is further used to expel the common envelope. However, this phase results in the tight binary black holes. In the common envelope case, the intermediate progenitor of the binary black hole is the black hole helium star binary in a close enough orbit that tides sufficiently spin up the helium star. And so the second born black hole may be highly spinning. In the chemically homogeneous evolution channel, one starts with a very close orbit of the period of a few days or less. Tides can efficiently synchronize the two stars and spin them up. This includes a strong rotational mixing in the stellar interiors that leads to a chemically homogeneous evolution. These stars never expand to become supergiants. Instead, they transition from the main sequence stars to the helium stars and further collapse to form two highly spinning black holes. LIGO and Virgo have already detected tens of galactic and extragalactic binary black holes, a few double neutron stars, black hole neutron star binaries. However, the network of ground phase detectors can only detect a small fraction of in spiral, a few seconds before their final merger. That means that the binaries that have already been, these binaries already have enough information about their prior evolution and detect the space-based detectors can detect a much larger part of their in spiral, but the horizon of the LISA is limited to the Milky Way galaxy and other nearby galaxies. So the statistical studies can help us distinguishing the formation channels of these binaries, and it can reveal their true origin. Such systems are electromagnetically invisible. So it's really challenging to estimate these binary black holes with LISA. Uh, we would like to answer the questions like, have there been any merging binary black holes in the Milky Way galaxy? And can we find any merging binary black holes in the Milky Way with LISA? Will the properties of these binaries will enable us to distinguish between their formation channels? In the rest of my talk, I will be presenting the preliminary results from our ongoing project. The approach we follow here is the binary population synthesis. We have used a synthetic binary black hole catalog produced at different metallicities using the newly developed Poseidon framework. Poseidon, among the other functionalities, can combine the rapid binary evolution codes, the cosmic in our case, and with the large grids of pre-calculated binary evolution models that are generated with the MISA code. These models have been calibrated to produce well the both rates and the distribution of the observed properties of binary black holes detected by LIGO and Virgo detectors. Then the synthetic catalogs have to be convolved with the metallicity dependent star formation history that would be appropriate for the Milky Way galaxy, and we use the LISA selection effects in order to finally produce the predictions of observable properties of the binary black hole. For our analysis, we use the fire simulation from the feedback relativistic environments, FIRE2 project, which provides spatially resolved information about the star formation history in the metallicity evolution of the Milky Way type galaxies, in their evolution and their evolution. Here we plot 1D and 2D distributions that we have extracted from the Milky Way simulation that we will then convolve with the synthetic binary population, binary black holes. What we see here in these histograms is that most of the stars are formed within 10 kiloparsec with the metallicities at or above the solar metallicities. But with the significant tail at lower metallicities down to 1/100 solar metallicity. And finally, the star formation rate is roughly constant with the time. Now, let's find the answer to the first question. By studying the metallicity dependent merger time scales of binary black holes. What I'm showing here is the distribution of earlier times for binary black hole population of different metallicities. These are the different colors for three considered channels. In all three panels, the dashed line represent the age of the universe, that is 13.8 gigayears. From these histograms, we can get the mean value of the merger time for each metallicity. From these histograms, we find that all the channels form the binary black holes that form within the Hubble time. But only for the metallicities for 1/10 solar metallicity, below 1/10 solar metallicity. In the chemically, in common and well-up channel, the binary black holes comes with the very short merger time scales, especially at the lowest metallicities. Whereas for the stable mass transfer and chemically homogeneous evolution, the binary black holes merge at time scales that are typically of the order of few gigayears. This coincides with our intuition because the stable mass transfer and chemically homogeneous evolution channel produce binary black holes at the larger orbital separations than the ones that are produced via common envelope channel. This is due to the lack of second unstable mass transfer that shrinks the orbit more significantly and than the stable one does. Now, let's compare these with the metallicity dependent star formation history of the Milky Way type galaxy. The heat map here shows the normalized star formation rate as a function of time and metallicity, whereas the red line and the associated error bars shows the median metallicities and their spread of the newly formed stars as a function of time scales. For comparison, with the three black lines, for each formation channel, we show the maximum metallicity at each. We can get from this plot that the binary black holes that would be merging by today. What with this figure tells us is that any merging binary black hole in the Milky Way must have formed in the first 4 to 6 giga-years of its lifetime, when star formation was happening at the low enough metallicities. And according by this figure, we could therefore say that the merging binary black hole systems can exist in the Milky Way. Now we move to the next question. Would it be possible to detect such emerging binary black holes with LISA? As we have already said, that LIGO and Virgo can only detect a small fraction of the last stages of the gravitational wave in spiral of binary compact objects. It has recently been proposed that numerous LIGO and Virgo sources will also be detectable by LISA. LISA will be able to detect binary black holes from the Milky Way and its neighborhood, evolving from their early in spiral stages. Interestingly, the sources that appears to be circular in the LIGO band may be centric in the LISA band, depending on their initial formation channels. However, the LISA will also be sensitive to the binary black holes that are too wide to merge within the human lifetime. Here I show the signal to noise ratio of the equal mass binaries of 10 solar masses as a function of its merger time scale using LISA sensitivity, and the dashed line represents the detection threshold of the signal to noise ratio, that is 8. We plotted it for different distances from 1 kiloparsec to 100 kiloparsec. And we can clearly see that, for example, a binary placed at 1 kiloparsec can have the merger time scale of 10 million years, and it would still be detectable with LISA. This would correspond to the present day orbital period of about few hours. So if even we will not be able to have an emerging binary black hole in the Milky Way galaxy in the LISA mission, we might be able to detect the galactic binaries at different stages of their in spiral that might enable us to distinguish between their formation channels. Moving to the last question, how would we be able to distinguish between the formation channels of binary black holes with LISA detector? What I'm showing here is the distribution of observable properties of binary black holes: chirp mass, chi-effective, and mass ratio that would merge within the next 20 years, and thus would also be detectable from a ground-based detector. All these signals would be super loud. Signal to noise ratio of tens to hundreds of the order of maybe 1,000, as I showed just before. So there is really no need to calculate signal to noise ratio of each one of them. What we see here is the two subchannels produce very similar distributions, except for the chirp mass, where the stable mass transfer gives support for slightly higher masses. It is interesting to compare these predictions with those of the population of binary black holes for the whole universe. The primary difference here is that the underlying metallicity dependent star formation history. The most striking difference is the lack of first spinning black hole in the common envelope channel in the Milky Way population. This is because the Milky Way might have formed relatively fewer metal poor stars compared to the average universe. And these are those metal poor stars that were formed that form fast spinning binary black holes. Of course, all these are purely theoretical interests, and the chance to observe the binary black holes merging in the Milky Way to merge in the next 20 years is almost negligible. What one wants to see is that the distribution of properties of binary black holes that would be detectable by LISA. These are binary black holes with an orbital period of up to few hours, and we identify them by estimating the signal to noise ratio following the methodology of Robson, and keeping those with signal to noise ratio greater than 8. What we find is that the distribution of observable properties is essentially identical to what I showed before. Based on the recent studies by Lambert, LISA would be detecting tens to hundreds of binary black holes, and our results are consistent. Our preliminary results are quite consistent with the Lambert studies, and as I'm running out of time, so I would put up my summary slides, and there are some takeaway messages, and I would like to have questions if there are any.
Okay, so thanks a lot, Rafia. So I open the floor to questions. It was a nice talk. So are there any questions? So how many such events you would expect probably per year? Very few, or can you give numbers, or?
It depends on the formation channels, and in our preliminary results, we are expecting 9 to 10 events for stable mass transfer, and up to tens to hundreds for common envelope channel. So the results are almost preliminary. So it's better to say that these are optimistic bounds.
But these are events in our galaxy, or all?
Yes, binary black holes in our galaxy.
Okay. Nice. Further questions?
Yeah, I was wondering if you could elaborate.
Please go ahead.
I was wondering if you could elaborate about this comment on the observed eccentricity as a way of disentangling different formation channels.
Mm-hmm. Sorry, what did you say?
Sorry, I was wondering if you could elaborate on this comment about the eccentricity and how that can disentangle different formation channels.
Did you understand the question?
Yes, it depends on it depends on the distribution of the underlying population, but eccentricities would be the key to find the difference between the formation channels, because they might give us some information about how they were formed, as compared to the other properties of the binary black holes. Eccentricities are quite important because the binary black holes that might form in the globular clusters or dynamical systems might have higher eccentricities as compared to the ones that are formed in the isolated formation channels. So the project is going on. So we expect that we will find something that will be informative.
That makes a lot of sense. Thank you.
Okay, thank you. Further questions?
Thank you.
Okay, seems not to be the case, then thank you very much. Now, according to program, we have some 5 minutes of break. So, but in any case, I asked the next speaker also to already prepare or to start sharing the screen so that we can, in 5-10 minutes, we can start immediately.
Hi, yeah, I'm the next speaker. Let me share my screen.
Okay, perfect. We see your screen perfectly.
Yeah,
I would just say we make a 5 minutes break and then we continue. Is that okay?
Okay, fine. Yeah.
Okay, I suggest that even if we are 5 minutes in advance, we start. So I see people is here. So please, Surai Kalita. Sorry if I'm
Yeah, it's correct.
Okay.
Yeah.
Go ahead again, a quarter of an hour plus 5 minutes. Okay.
Okay. Yeah, thanks. Yeah. Okay, good morning, good evening, wherever you are. So today I'll be talking about continuous gravitational waves observation from white dwarfs to constant modified gravity theories. So I'll come to the meaning of each of these terms when I'm going over the talk. And these works have been published in a series of papers with the collaboration of Bani Brata, who is my PhD supervisor, Tushar from ISC, and Thomas Bullock from University of Warsaw, and Christopher Taut from Cambridge Universities. So, what is a white dwarf? We know from basic astrophysics that if a progenitor star has a mass of around 10 plus minus 2 solar mass, there are a little bit uncertainties in this range. At the end of its lifetime, that means when the nuclear burning is over and everything, and after some stages, say red giant, etc., finally those stars becomes white dwarf. And in a white dwarf, because it has degenerate electron gas, basically the white dwarfs are temperature of the white dwarf is very less compared to the Fermi electrons. So we say that the inward Fermi temperature, sorry. So the inward gravitational force and the force due to outer degeneracy pressure balance each other to attain a stable equilibrium. And let's say if there is a white dwarf and if there is some binary partner, say some star, main sequence star, it will start pulling matter out from the star due to white dwarf's high gravity. And eventually its mass starts increasing. And what happens, Chandrasekhar showed in 1930s for his famous discovery that the white dwarf can have maximum mass of 1.4 solar mass. If it's gaining mass more than 1.4 solar mass, this pressure balance no longer sustains, and it bursts out to produce type 1a supernova. And we all know that type 1a supernova are very much used as standard candles to measure luminosity distances for cosmological objects. So in that sense, type 1a supernova is important, and because of that type 1a supernova, even Chandrasekhar mass limit is also important. However, what happens, say recently, say Howell et al. In 2006, they have shown that some supernova have extremely high luminosity, such as this one. In a white dwarf, when it bursts out to produce type 1a supernova, it may have maximum this much nickel mass, say around 0.85 solar mass. However, they have observed some white dwarf whose luminosity is basically they have observed, and when they calculate, they found that the nickel mass turns out to be nearly 1.3 solar mass. So once they're going to back calculate from the luminosity to the mass of the white dwarf from which this type 1a supernova was produced, it turns out that the mass of the white dwarf turns out to be nearly 2.1 to 2.8 solar mass. And similarly, some other white dwarfs have been observed on this side with very low mass. Those white dwarfs even burst at, say, at 0.5 solar mass even. So those things basically, both these cases, Chandrasekhar limit is violated. Now, in this case, it doesn't even reach 1.4 solar mass, and in this case, it exceeds 1.4 solar mass. So how to explain this Chandrasekhar mass limit violation? People have proposed many models, at least 50 to 100 models. But in this talk, I will be talking about only 3 models. One is rotation, one is magnetic field, and one is modified Einstein's gravity. I'll be talking about only the FR gravity, and there are many other models. Now there is a problem. Since there are so many models, it's become almost impossible right now to figure out which one is the correct theory, or and so on. And because of that reason, it's getting very much important to detect this kind of white dwarfs, these white dwarfs, peculiar white dwarfs, to observe directly. And so far, none of these white dwarfs have been detected directly from any optical observations or any electromagnetic observations. So how to detect them directly? So I'll show that gravitational waves will be one of the probes. And as shown here also, not only those at least 15 or so, at least super Chandrasekhar white dwarfs have been predicted from these luminosity observations. And those usually violates the Phillips relations also from this figure. So now what is inner white dwarf? Inner white dwarf, basically the structure of a white dwarf can be determined from the 2 equations. One is the pressure balance equations and one is the mass balance equation. And both these equations has to be supplied with this equation of state, some equation of state. And for a white dwarf, because it has degenerate electron gas, it has to be given the Chandrasekhar equation of state, which is given in 1931. And once we solve these 3 equations, we obtain the mass radius relation of the white dwarf, which shows that the maximum mass can be 1.4 solar mass. Anything after, when the curve turns back beyond the maximum mass, those white dwarfs are unstable, and they are unstable in terms of radial perturbations. So those white dwarfs may not exist. So maximum mass will be exist up to only 1.4 solar mass. However, if we want to show the violation of the Chandrasekhar limit, that means it has to violate this 1.4 solar mass, one needs to modify or change this either of these 3 equations. So I'll show that the FR gravity in place of Einstein equation, where it's R gravity, basically, if we use F of R gravity theory, say in this form, my pressure balance and mass balance equations are modified. So black terms are as usual GR term, but these extra terms are coming from this modified gravity term. And you can see if alpha is 0, of course, we reduce to again earlier TOV equations. So with this, if we just plot again the mass and radius, you can see that this is the Chandrasekhar mass radius relation, and this is our FR gravity mass radius relation. As I have said, it's at the low density limit, basically they merge, but at the high, as its density is increasing, after some point it turns back. And I have said that as the turns back, because here in this turns back, mass decreasing as the central density is increasing, this branch is unstable. So we obtain one limiting mass, which is the sub-Chandrasekhar limiting mass. And after this, also it's having the usual behavior, that is mass increases with the central density increases. So this portion is the probing the super Chandrasekhar white dwarfs. And the parameter alpha, here we have given the constants from this paper, Naffenzetzer, with this bound given by gravity probe B. And accordingly, basically with this FR gravity model, we can directly, with one FR gravity model, with the same value of alpha, gamma, etc., we obtain the sub and super Chandrasekhar white dwarfs. Now, of course, this is a theoretical mass radius curve. Can we observe them directly? And as I have said, I'll try to do it using gravitational wave. We know any objects will be emitting, any systems will be emitting gravitational radiation if it has a time-varying non-zero quadrupolar moment. And of course, as the previous speakers have also shown, that from the merger events, gravitational waves have already been detected. However, there are some other gravitational waves, the other types of gravitational waves called continuous gravitational waves, which are emitting continuously over a period of time with almost similar frequencies and amplitudes. And I'll show that in this case, I'm not talking about the binaries, but I'll be rather talking about isolated compact objects, so white dwarfs. If they are triaxial, they can emit continuous gravitational waves. Now, what is a triaxial white dwarf? Triaxial white dwarfs means the moment of inertia about x-axis, about y-axis, and about z-axis. That means moment of inertia about any three mutually perpendicular axes are different. If a system has such a configuration and it has a rotation, that system can emit gravitational waves. And for example, let's say this is a kind of configuration where it has magnetic field, and z direction and z prime is the direction of the angular frequency. It has an angle chi, and our detector is here, which is making an angle I with the rotation axis. Then this kind of objects can emit gravitational radiations. Now, since I am using FR gravity theories, it's very important that FR gravity theories not only has two tensorial modes, but also one scalar mode. So two tensorial modes, we always know they are plus and cross polarizations. That's also present in general theory of relativity. However, the extra scalar mode is present only in FR gravity. If we go to other higher order theories, we may have another more number of degrees of freedom, more number of modes. However, for white dwarfs, which we have considered, we have actually shown that the scalar mode is exponentially suppressed with this factor, where R is the distance between this source and the detector, and it will be in parsec scale. So this factor is huge, and because of this scalar mode, it will never reach us. So we have only these two frequencies, these two modes, and you can see in case of magnetic field, it emits only in two frequencies. One is omega rotation, and one is 2 omega rotation. And these are basically the amplitudes formula. So this structure is basically for magnetic white dwarfs. Now we may have magnetic field in different directions. For example, we have toroidal field configuration, we have poloidal field configurations. In case of toroidal field configuration, the star will become an prolet-like shape, like a rugby ball shape. Whereas if the star has poloidal field, it will have an oblate-like shape like this. So in this way, basically magnetic field deforms a white dwarf. Next, one more possibility is, say the magnetic field is very weak. In that case, these deformations will not be very promising. However, the white dwarfs may have a little bit roughness at its surface, so presence of some mountains-like structure and so on. And it can be shown that the maximum height of a mountain on any surface is given by this formula, where Z is the element present at the surface. So if we consider helium white dwarf, Z will be 2, and if we consider hydrogen white dwarf, Z will be 1. So, and because of this reason, we always find that the height of these mountains are very, very less than compared to the radius of the white dwarfs. It can also be seen from here that the height of the mountain for different masses of the white dwarf is around 1 to 10 kilometers, whereas we know the radius is around 1,000 or more than 1,000 kilometers. And in these configurations also, we obtain this that moment of inertia about all three axes are different from each other. So it makes it a triaxial system, and it will emit gravitational waves. And both the modes of polarization are given by this formula. But here you can see it emits not only 2 frequencies, but also in 3 frequencies. One is 2 omega rotation, one is omega rotation plus omega precession, and then one is 2 omega rotation and 2 omega precession. And these are various formula, and the exact derivation is given by this famous Megoret's book. So now if we just plug in all these formulas and everything, and we take the data from online basically, and we plot with the various detectors curve, basically power spectral densities, and with various time scales, it can be seen that if those white dwarfs are weakly magnetized white dwarf, or even they have some surface roughness, they can be detected, say, by BBGO, DESIGO, etc., even by maybe the Einstein telescope, but they cannot be detected by LISA anymore. Even if I take this time scale of integration to many years, still it is not possible to detect it by LISA. So, but let's say it's detected by any of these detectors. Once some white dwarfs are detected, we can immediately obtain its amplitude and its frequency. And using this formula, we can obtain the moment of inertia of these objects. And once we obtain the moment of inertia, we can actually predict the mass of these objects. And if the mass is super Chandrasekhar white dwarf, basically mass is something different than the Chandrasekhar limit, then actually this kind of gravitational waves can confirm the existence of those objects directly. And also it can be seen that because these objects are weakly magnetized white dwarf, they lose their energy through dipole and gravitational wave luminosity, but its dipole luminosity is less because of less magnetic field. these white dwarfs emit these gravitational radiations for many years. You can see for 10^10, 10^11 years, which are much longer time range. So we'll not have any problem in detecting such white dwarfs if they are there. Of course, low magnetic white dwarfs are there. So even if super Chandrasekhar white dwarfs are not detected, but at least less magnetized white dwarfs, which so far have not been detected in gravitational waves, they can be detected by these detectors, but not by LISA. But what to do with, but can we detect by LISA? And yes, of course, let's say if we go for magnetic field, the central magnetic field, let's say nearly 3×14 Gauss, and then if I have just plotted these things, remembering that we have used stack slide method with time stack with 1 hour, we find that within 1 year of time scale, or within 1 year of integration scale, LISA can detect this highly magnetized white dwarf. But if the magnetic field is decreased, even if this much, even LISA or not even Tian Queen, none of them can detect these white dwarfs. But of course, other detectors can of course detect them. So to conclude this, that magnetic fields and rotation can explain the existence of the super Chandrasekhar white dwarfs, and modified gravity, as I've shown, can explain both sub and super Chandrasekhar limiting mass white dwarfs. And peculiar white dwarfs, these white dwarfs have not been detected directly so far. They have been only explained through the observations of luminosities of type 1a supernovae. However, to obtain detect these objects directly, gravitational waves can be one of the probe to detect these objects. And each of these theories, of course, as I have shown that there are many theories in modified gravity magnetic field, and there are many more theories. They give different mass radius relation, and to single out which theory is the correct one, we need the masses and radii of the objects. And as I have shown that gravitational waves can detect these objects will be able to detect directly, either by LISA or by other detectors also. And of course, LISA can only detect them within 1 year if they are within 100% scale and they have high magnetic field. But other detectors can also detect them probably much easier way. So with this conclusion, these are the reference, the series of papers we have published. Last one is under review. So thank you.
Okay, thank you very much, Surajit. Any questions? Everything is clear? Okay, then again, thank you very much.
Yeah, thanks.
And then I call the next speaker on the floor. So please share your screen. This should be Alexander Criswell, if I'm not okay. Perfect. Okay, I suggest we start. So you have 20 minutes, 15 plus 5. Please go ahead. Thank you.
Great, thank you. So hi, I'm Alexander. I'm a PhD student at the University of Minnesota in the Minnesota Institute for Astrophysics, working with Big Bandage. And yeah, I'm going to be talking to you today about exploring anisotropic gravitational wave backgrounds and foregrounds using LISA. Yeah, if I could get my slides to advance. There we go. Okay, so this is based on a paper that has been submitted, currently under review, and you can find a preprint of it on the archive called Mapping the Gravitational Wave Sky with LISA, a Bayesian Spherical Harmonic Approach. This paper is in collaboration with my colleagues Shram Banajiri, Tommy Kwan, Buk Mandich, Joe Romano, and Stephen Taylor. So I've said the word stochastic gravitational background a couple of times now. Let's dig into what these actually are. The basic idea is imagine that a single gravitational wave signal of the kind that have been detected so far, like a binary black hole merger, is a single person talking in a room. You can usually, if you're standing in the same room as them, you can make out what they're saying pretty clearly. There's no distractions. There's nobody talking over them. It's just one person talking like I'm talking to you right now. However, say you're in the same room, but now there are 1,000 people in that room, and they're all talking. Everybody has something to say. Everything's overlapping. You can't actually make out what any single one of these people are saying, But the overall volume of the room can tell you something about the number of people in the room. If you hear more from one direction than another, that can tell you about the distribution of people in the room. And this would be a superposition, to extend the analogy back to gravitational waves, would be a superposition of many unresolved gravitational wave sources. There are, generally speaking, two types of stochastic gravitational wave backgrounds, cosmological and astrophysical. Cosmological backgrounds arise from the early universe. Inflation can have a possible stochastic signal, as can phase transitions in the early universe, cosmic string deformation. And largely, cosmological backgrounds should be isotropic at the scales accessible by LISA. They may have small anisotropies, but nothing that we should be able to detect with the resolution that LISA provides. Astrophysical backgrounds, on the other hand, are the superposition of many individual astrophysical events. So a good example of this that we'll come back to later is the combination of every unresolved white dwarf binary in the Milky Way, or every massive binary black hole merger that we're able to detect in the universe. And the cool thing about these is they should reflect the spatial distributions of their component sources, and as such, they can be anisotropic, which is to say, if the events are happening in certain places on the sky, we should have more gravitational wave power coming from those areas of the sky, as opposed to areas in which these events are not taking place for whatever reason. So a good example of a very anisotropic a very anisotropic stochastic signal would be the double white dwarf galactic foreground, which is the combined choir of all the unresolved galactic double white dwarf binaries in the Milky Way. And this is actually such a strong signal that it sits above the noise. This is why we call it a foreground instead of a background. You can see it in the gray area down in the plot on the right, and you can see where it actually pushes above LISA's noise curve. So it's this really interesting situation because it traces the white dwarf history and distribution of the Milky Way and has a lot of interesting science that's connected to it. But on the other hand, it is a source of noise for the detector and can drown out other potential gravitational wave sources. So we're interested in it not only because we can do cool science with it, but also because we want to characterize it really well so that we can get rid of it for other searches. It predictably, because it's coming from galactic binaries, it is going to trace the galactic plane, and as such is going to be highly anisotropic as seen on the sky from the solar system. So how are we going to explore these things? What am I talking to you about today? I'm talking to you about something called the Bayesian LISA pipeline, also known as BLIP. It's a project that I've been working on for a while now. And it's a Python pipeline for end-to-end data simulation, Bayesian analysis with LISA. It's available in an open repository on GitHub, as well as pip installable via pip install GW. We've put a lot of stuff into this pipeline. We can do time domain simulations of instrumental noise and gravitational wave signals, modular gravitational wave signal and likelihood models. It's very easy to write your own signal in here. If you're interested in using the pipeline for something that we don't already have set up, it plugs right in. We can do the Michelson and XYZ and AE and T time domain interferometry channels. We have both a stationary model as well as heliocentric rigid body orbital models for the satellite orbits, and the pipeline can perform Bayesian inference via your choice of the MC sampler or the dynasty nested sampler. So overall, it can perform isotropic and anisotropic analyses for stochastic gravitational wave backgrounds and foregrounds. But how? When we're talking about anisotropies, right, we have to remember that it's going to be something that is, well, anisotropic on the sky. It's spread out, it has some weird shape, it's generally hard to characterize. So we have to approach this with a little bit of subtlety. The way that this is often approached is we just split the gravitational wave background into some frequency dependence and spatial distribution. We don't usually expect the frequency dependence to be in any way dependent on the spatial distribution, so we can do this. And we'll oftentimes make the frequency dependence a power law and then expand the spatial distribution with spherical harmonics. But you have to be very, very careful when you're doing this, because gravitational wave power is power. It's a physical quantity that has to be non-negative. But spherical harmonic expansions do not have that constraint. The solution that has often been applied in the past is to say, okay, I'm going to check the sky map that I'm making with this particular set of spherical harmonic coefficients and see if any point on that sky map has negative power. If it does, I'm going to set the posterior probability to 0 and go on with my life. This is really inefficient. It's computationally expensive. You're having to do this for every single step of the sampler that you're running many, many thousands of times. And on top of that, it doesn't even work because you can always go to a finer grid. And if the tiny littlest point of negative power exists on your sky map at a smaller resolution than you have access to, you should be throwing that sky map out, but you're not. So let's get around this. My colleague Sharon came up with a very clever solution, which is to say, okay, let's take a square root of our spherical harmonic expansion and then expand that. So we're doing an expansion of a square root of an expansion. But if we want the first expansion to be non-negative, we just need to have its square root be real, right? You square it. If there's any imaginary component, you have the possibility of negative signs. But if it's just real, you square it and it has to be positive. We all know this. And this is actually a really easy characteristic to implement in a spherical harmonic expansion. If you want it to be real, there's the characteristic on the BLMs, and it's very straightforward. So we can write this spherical harmonic expansion as a square of a different expansion that follows that limitation, and our problems are solved. On top of that, this product of two different, well, this square rather of the second expansion can be expanded as a sum over spherical harmonic using the Clebsch-Gordon coefficients that we're all familiar with from quantum mechanics. If you're interested in that, I do have an extra slide on it, but it's a lot of math, so we're going to skip it for now. We can come back later if people are interested in it. So what do we get out of the other end? So this is a validation run. We injected a highly anisotropic, it's a really weird shape on the sky. It's unphysical. I can't think of anything that would actually look like this, but it's a very good probe of how well our pipeline can actually recover these sorts of signals. And as you can see, it recovers them extremely well. It traces the anisotropies almost perfectly, has a really good fidelity. We get good results out of the anisotropic recoveries using this method. This is the sort of actual result that we get to make those sky maps, which you'll note were median sky maps. It's a very high dimensional space. This is actually one of the lower dimensional versions that we're able to do. This keeps to a pretty low Lmax, but still ends up being quite high dimensional because you have to deal with all of the BLMs and their associated phases. If you're interested, I mean, you can look at the different recoveries. The little green lines are the true values that we injected, and you can see that they're being recovered quite well. More specifically, this top left-hand corner covers the specific parameters of the frequency content of the gravitational wave signal, along with the noise, the position and acceleration noise parameters of the detector itself. All of them are covered, and if you check out those error bounds, they're actually recovered not only accurately, but very precisely. So let's take a look at an actual more physical case. This is a toy model of the galactic foreground that's based on work by Katie Brebeck and her collaborators. And we've taken their model. I've got an extra slide on this too, if you're interested in the specifics of the model. But it basically, it's not a full population evolution thing or anything. It's just, well, you know, assign some exponential profile to the double white dwarfs in the galactic plane, put them all out there, get their gravitational wave power, project it on the sky the way we would see it, inject that, and then see what we get out of the other side. And it turns out that we actually do pretty well. We're obviously missing this area on the left, which is the outskirts of the galaxy away from the galactic center beyond us, where the signal is very weak, so we don't pick that up extremely well. But the galactic center is actually recovered with a fair bit of fidelity. We did a coherence test on these, and for the double white dwarf foreground, or at least this toy model of it, we're able to recover this sky map with 95% coherence to the injected sky map. So I think I'm starting to run out of time here, so let's look at where we can go from here. What we've essentially developed is a tool. It is a tool that can look at anisotropies on the sky and characterize them quite accurately. But we're not doing any real meaty science with that yet. But there's a lot of things that we can learn now that we have a tool to analyze anisotropic gravitational wave backgrounds and foregrounds. For example, answering that question of like, what can we learn about the Milky Way from its white dwarf foreground? Its history, the white dwarf distribution. There's a lot of interesting science buried there, and we can start to learn about it. Can we actually start looking to see if we can have a chance of detecting the unresolved white dwarf binaries from Milky Way satellites, like the Large Magellanic Cloud? Can we look out beyond our galaxy and detect and characterize anisotropies in astrophysical backgrounds from MREs or massive binaries due to the large scale structure of the universe? Can we reach that kind of resolution, or is it too computationally expensive? And then really all of this boils down into one question, which is my big next project, is how do we actually go from these spherical harmonic amplitudes and phases, which is what our pipeline produces, into estimates of physical quantities, because it's not a very simple translation and is going to require a little bit of a subtle approach. On top of that, this is a Bayesian pipeline, which means it's very easy it's much simpler than in a frequentist approach to perform simultaneous inference of multiple different backgrounds and foregrounds. If we have, say, an isotropic gravitational wave background from inflation and the white dwarf foreground, can we recover both of these accurately at the same time? On top of that, to relate to the galactic foreground, can we actually, like I said earlier, characterize it well enough to subtract it and remove its noise contribution for other sources? And then finally, there are some things with the detector simulation that we want to make more realistic in a way that nobody else, as far as I know, has actually done before, which is going that extra mile and dealing with the fact that LISA is not going to be a nice fixed triangle all the time. The orbits are going to add flexing into the arm lengths, and the time domain interferometry approximations that pretty much everybody in the field has been using are going to start to break down outside of that limit. Vallisneri et al. Have come up with a really clever solution to this called TDI Infinity. Go read the paper, it's great. And we want to incorporate that as well to start performing TDI and doing these sorts of analyses in really the full simulation of what LISA will be doing. So here are the references. You can see some acknowledgements and thank yous there. And then I'll put my summary slide up and open the floor for questions.
Thanks a lot, Alexander, for the nice talk. I open the floor to questions. Any question? Everything is clear?
Maybe I would maybe I would like, it's not a question, but I would like to ask, are you planning to participate in the Thesa data challenges as well?
Yes, yeah. And we participated in the last one. I think the results are out by now. I'm not sure. But we did participate in the one that was last year. Time has kind of lost meaning. And something that we're interested in once we have the capability to do it is looking at some of these mixed signal MVCs that they're starting to put out with that.
Great. Thank you.
Mm-hmm.
Thank you. Further questions? Okay, seems not to be the case. Then thank you again very much for this nice contribution. Then I ask the last speaker on this session. This is Shu Yan Lau, or sorry if I pronounce it wrongly.
Yes, that's correct. Yeah, that's
okay,
correct.
Then thanks. And then please share your screen and you start. So you have, as usual, about 20 minutes, 15 for talk and 5 for the questions. Thanks.
All right. Thank you very much. All right, so I'm going to get started. So hi, everyone. So today I'm going to talk about my project with Professor Ken Yagi and Professor Phil Aris. And I'm a PhD student from the University of Virginia. And we are currently working on constructing a new waveform model for eccentric double white dwarf binary systems for LISA. Right. So to begin with, I would like to give some background about our motivation of this project. So as you all know, the galactic double white dwarf systems are one of the most promising sources for LISA. If they're compact enough, they lie within the LISA frequency band, which ranges from 10 to the -4 to 10 to the -1 hertz. And this kind of double white dwarf systems are abundant enough inside our galaxy, but we expect most of these systems are in a circular orbit. So why do we want to study the eccentric double white dwarf systems? Answer to it is by one of the papers by William Zittel on 2007. They consider simulation results of the globular clusters inside our galaxy, in which they found that there can be quite a handful of eccentric double white dwarf systems that is within our galaxy and lies within the detectable range in LISA. And by studying these kind of systems, we can learn more about the dynamical formation channels, and this kind of motivates us to construct a efficient and accurate waveform model for double white dwarf systems. All right, so before I start introducing our model, I would like to give a little bit of introduction to some previous work, again by William Zittel on 2008. And in their study, they consider a semi-analytical waveform model for eccentric double white dwarf systems. By semi-analytical, it is essentially basically a harmonic decomposition, or call it a combination of Fourier series expansion, which express the waveform in terms of some Fourier amplitudes and some phase term, and with some precession afterwards. And in their model, they consider Fourier coefficients using the analytic expressions for a Keplerian orbit. And in order to include also the non-Keplerian forces, they include the analytical expressions for obtained from orbital averaging over the perturbed Keplerian orbit in their precession term. In specific, they have included the leading general relativistic effect, the first post-Newtonian effect, and also the equilibrium tidal effect, and also the self-rotation of the white dwarf. And other than that, in the phase term, they have also included orbital decay effect due to gravitational radiation. And in our work, we're currently trying to improve their model by using numerical integration to determine the Fourier amplitudes, Fourier coefficients, and also the precession rate. And on the orbital decay part, we want to add additional effects due to tidal friction. In this way, we can, based on the waveform model and the detection, we can try to constrain the internal dissipation mechanism inside a white dwarf. And there is also an ongoing part in this project that we're trying to improve the tidal contribution by including dynamical tide in the equation of motion. But so far, we still haven't got any concrete results yet. So let me start introducing our waveform model. So basically, the waveform model is based on the quadrupole formula, which states that the metric perturbation depends inversely to the distance from source, and also the second time derivative of the quadrupole moment tensor. For a planar system like a binary white dwarf system, the quadrupole moment tensor only has 3 components, basically the 1, 1, 2, 2, and also the 1, 2 components. And so if we are able to integrate the equation of motion and obtain the trajectory over time, then we are able to determine this quadrupole moment, and from that we can obtain our waveform in time domain. So now it is the orbital equation of motion we consider. Basically, the acceleration depends on 3 different forces. The first one is basically the Newtonian gravity term. And then we also have the post-Newtonian correction to it, which goes as mass divided by separation compared to the Newtonian gravity. And we also have the equilibrium tidal term, which goes as 1 over r to the 5th higher than the Newtonian gravity term. And also it contains a tidal deformability factor, which we abbreviated as lambda. And here lambda is basically telling us the ability for a white dwarf to deform under an external tidal field epsilon. And this lambda parameter also scales with the radius of the white dwarf to the power of 5th order. And on the right-hand side, I'm showing for one sample orbit, the size of the post-Caparian parameters, that is the correction parameters described above. And the black curve represents the post-Newtonian parameter, and the blue curve represents the tidal deformability parameter with the dimension taken out. And here we can see that as the mass of the system increases, the post-Newtonian term becomes more important. And for the tidal term, it decreases with the mass, because as the mass of the system, mass of the white dwarf goes higher, the radius actually shrinks. So these 2 effects are expected to both be important in the orbital equation of motion. And by integrating this orbital equation of motion, we are able to obtain the quadrupole moment, and from that we can obtain our waveform. But directly integration of the orbital equation of motion is not an efficient way to obtain the waveform. So we are considering a similar approach to the previous work, which we consider a Fourier series expansion. And for this model, we call it the Kluge model. And basically in this model, we have some numerical coefficients to determine by integrating the orbital equation of motion for one full complete orbit. Basically, there are the Fourier coefficients and the orbital frequency and the precession rate. For the Fourier coefficients, it requires some attention because for now, the orbital trajectory has some precession in it, and the quantities, the quadrupole moment quantities, they depend on both the radial and the polar coordinates. And in the case with precession, these 2 quantities will have different periodicities. And so we can't directly carry out a Fourier series expansion with one single frequency. So in order to incorporate this effect, we'll have to go into a precessing frame that cancels out the precession rate. In that frame, we can carry out the numerical Fourier series expansion to obtain the Fourier coefficients. So this is how we obtain the so-called Kluge model, which only includes the conservative forces in the orbital equation of motion. So far, we have neglected the effect of orbital decay, and we are going to insert it later on. And so for now, we just want to compare this model with Willem's model. And in Willem's model, they consider for the Fourier amplitudes, Fourier coefficients, they consider the analytical expression derived from a Keplerian orbit, which basically it's, as an example here, I'm showing one of the components here. And it basically depends on a combination of Bessel functions. And in our case, we determine these coefficients numerically. And here I'm showing for one particular orbit, for one particular system, double white dwarf system, the fractional deviation between our model and Willem's model. And it shows that for this Fourier amplitudes, there are certain harmonics that this fractional deviation can go as high as 30%. And next, I also want to compare the precession rate between our model and Williams' model. And in Williams' model, they consider some analytic expression derived from a perturbed Keplerian orbit for the forces they have included. Here, I'm including the equilibrium tidal effect and also the first post-Newtonian effect, same as the orbital equation of motion I considered. And here the figure shows the fractional deviation between our model and Williams' model. And for this particular case, with the masses of the white dwarfs to be 0.6 solar mass and eccentricity with 0.5, I plot the fractional deviation of the precession rate as a function of the orbital period. So for a really close orbit, that is, the separation is really small here, the fractional deviation can go up to around 1%. And I leave a remark here that for a observation, for a signal that lasts for, say, 1 year, the resolution power is enough to be able to resolve this kind of difference. So here I've just emphasized that this kind of difference might be important when the orbit is, the separation of the orbit is small enough. So, so far I've explained our Kluge model, which includes only the conservative forces. And now I'm going to explain how we are going to include the orbital decay effect. So the orbital decay effect of a double white dwarf system is expected to be small. So we carry out a Taylor series expansion on the phase term up to the leading order. And orbital decay effects enters in the first correction term here, which enters as the rate of change of the orbital frequency. So there are two contributing factors we have included in our model for this rate of change of orbital frequency. First one is gravitational radiation effect, which enters in the 2.5 post-Newtonian order. And the second is the tidal friction effect. And here we employ Hutt's model given in 1981, which is a constant lag time model. In this model, basically, I'm just schematically explaining it here. Basically, we can consider that the tidally deformed white dwarf is spinning at a rate that is lagged behind the instantaneous direction of force by a constant lag time, that is tau. And from that, there will be extra forces and extra torque exerted on the white dwarf that causes the orbital decay effect. And according to the formula in Hutt's model, this decay effect basically is proportional to the tidal deformability and some function of eccentricity and the white dwarf spin, and also a constant lag time. And this lag time here is what we treat as a parameter. And by studying the signal from a double white dwarf system, there is a chance we can place constraint on this lag time, which in turn tells us information about the internal dissipation mechanism inside a white dwarf. So here I've given the way we construct the eccentric double white dwarf waveform. And here I'm showing one of the sample waveform using the above described method. To be specific, I've included 3 different waveforms to show the features inside such a gravitational wave signal in the Fourier domain. So in the gross scale shown in the left-hand side here, we can see that both the waveform from a Keplerian orbit, the waveform from a Kluge model, that is the model with only the conservative forces without the orbital decay effect, and also the red one includes all the effects described above. And all of these models look like a combination of monochromatic signals in the gross scale. But if we zoom into the first peak here, we can see a Keplerian, for a Keplerian waveform, each harmonic is a single peak, but when there is precession effect, each peak is further separated into 3, with the difference between them proportional to the precession rate. And if we have included the orbital decay effect as well, each peak will be further spread out as a chirping signal. So basically, this tells the feature of the waveform, expected feature of the double white dwarf waveform. And next, I would just I just want to talk a little bit about the current status of the work. So we have already included the conservative forces and also the orbital decay effect, but we want to further explore what if we include the overall tidal effect, that is just not just the equilibrium tidal effect, but also the dynamical part of the tidal effect. So by dynamical tide effect, it means the frequency dependence response of the white dwarf. And this response basically depends on the natural frequencies of the white dwarf itself. And here, I just want to emphasize that the equilibrium tidal effect is basically the low frequency limit of the overall tidal effect. Basically, it is valid when the orbital frequency is much smaller than the normal mode's frequency inside the star. So in order to solve for the complete overall tidal response of the star, we'll need to also solve for the equation of motion of a mass element inside the star. And from that, we can know the overall change in shape of the star at a given time. And from that, we can calculate the its back reaction onto the orbit and obtain this overall tidal force. And so far, we haven't got any concrete result yet, but we have tried to integrate it for several orbits, and we find that this dynamical tidal piece has the potential to give an extra 10% of precision into our signal. So this basically tells us that this dynamical tides can be significant in certain scenarios when the orbital separation is small enough. So this is basically the end of my talk. And so to summarize, we have constructed a semi-analytical waveform model that is an improvement based on the previous Williams model. And we have also compared it with the previous model and find that in terms of amplitude correction, it has around 10%. And for the precession rate, it improves by around 1%. And we are currently also working on the dynamical tidal force, and it can cause around 10% of difference in precession as well. And thank you very much. And I'm happy to take any questions.
Thanks a lot for the nice talk. So questions, I saw already Alexander Criswell, so unmute yourself.
I'm just applauding. A good talk.
Oh, thanks.
Okay. Further questions? So maybe how long will you take this to work out all your program?
Oh, you mean the for a waveform for say if we are considering for the LISA observation time 4 years of a waveform, I guess for the Klutsch model, I guess it takes around several minutes, right? But if we are directly integrating the orbital equation of motion, it will take maybe days, I guess.
Okay. Other questions? So seems not to be the case. Then I would like to thank all speakers for this very nice session of very high quality. And I wish you also a good rest of the day or evening, depending on your time zone. And also stay tuned on the Marcel Grossmann meeting. Bye to everybody. And thank you again very much. Bye-bye.